Today we're going to start talking about the mole. And when we talk about a mole, we're not talking about a little fuzzy critter that tears up your yard, so to speak, but it's actually a chemistry term that after today you're going to go, oh yeah, I know what a mole is. And if you talk to anybody else that has had chemistry, and did well in chemistry, they'll know what a mole is. It's actually a value. It's a number. It's a number without a unit. Until you put a unit on it, that number actually has no meaning. But when we talk about a mole, it's a standard method in chemistry for communicating how much of something you have. So when we talk about a mole, it is that number right there. Where it is. 6.02 times 10 to the 23. Now that's a big number. That's a really big number. If I had that many dollars, well, I'm just going to tell you, there's not that many dollars that exist because it's a large number. So we can't just say, we can't talk about in terms of how many particles we have, so we generally do it in how many moles we have. Now, and I'm trying to remember, where are the blanks? Is that a blank? Okay. Go up, right here. You have that? Basic entities. Okay. And also you'll hear this number, let me blow this just a little. You'll hear me refer to this value as Avogadro's number. Okay, it's not an avocado, the thing you make guacamole out of. But Avogadro is a person. It's one of those dead chemists, old dead guys. And he's the one that came up with this reoccurring value when he was doing calculations. So he gets credit for this 6.02 times 10 to 23. And in some cases you might see this written as 6.022 times 10 to the 23. Tomato, tomato. When you get that much, it just doesn't matter if that 2's there or not. Now, when we talk about this value, it's kind of nice, and you should be able to type that in on your calculator, and we'll do that here very shortly. I have, and I don't mean to be bragging and showing off here, but I want to talk about how much a mole actually is. Okay. What I have in my hand are 10 dimes. Yes, I don't like to show off. Okay, but a dime is really unique, and if you hold it up like that, some of you can see the dime that's in my hand. A dime is really unique because the width of one dime is 1 millimeter. And I don't know if that was on accident or on purpose, but if I had 6.02 times 10 to the 23 dimes, I'd be very, very rich and probably not standing in front of you right now. But if I take 10 of those dimes and stack them together, what is my length now? 10 millimeters, which is also equal to 1 centimeter. Very good. So, I know it's early in the morning here, but let's say that I had that many dimes and I were to stack it on the desk here in a nice straight column. Okay. So I had that many dimes, that many dimes in a nice straight column. It wasn't swaying, and I was able to stack them all up. Number one, it'd probably take me a long time to count them. But if we use our conversion, we can determine that it actually would be 3.74 times 10 to the 17 miles in length. Okay. So my question to you is, well, how far is that? Well, we know that 9.3 times 10 to the 7 miles is the average distance from here to the sun. Okay. So 9.3 times 10 to the 7, are we like almost halfway there? Half of 17, a little under half, maybe. 3.7 times 10 to the 3.7 times 10 to the 9 miles is the average distance from Sun to Pluto. Now again, this is hard for me to visualize. If I can't walk it, run it, drive it, these numbers don't mean anything to me. 5.9 times 10 to the 12 miles is the distance that light travels in 1 year. Again, I'm still talking about a mole of this, dimes. And they be willing to bet that most of you can't even see that dime as I'm holding it up. from where you're sitting. That's how thin it is. Okay. And so it says, so 1 mole straight column of dynes is equal to 3.7 times 10 to the 17 miles, which is equal to 63,400 light years. Our Milky Way galaxy is only 40,000 light years. So again, I'm talking about a mole. 6.02 times 10 to the 23 of these dimes stacked up. Pretty long. Okay, and again, I can't visualize this. I don't know really how far that is. I just know it's a long distance. So when we talk about Avogadro's number and putting it in perspective, in this graduated cylinder I have water. Actually, I have Avogadro's number of water molecules. I counted it out this morning. No. You'll find out how I was able to do that, but I have 6.02 times 10 to the 23 molecules of water in this graduated cylinder. So when we talk about the size of atoms and molecules, we can say that they're really, really small. So when we look at the number of atoms and molecules, it's something that we can't comprehend. We can't count. There's a lot of things that we can't do with that number except calculate. So one of the nice things is that you have your periodic table. And the numbers, let's actually blow this up. We're finally going to get to use these numbers down here. Over here. So when we look at these numbers down here, these represent what again? Molar mass. So we technically haven't used it yet. And we're talking, this is February, early February, and we haven't used these numbers on the bottom. But these numbers down here are what's called molar masses. If I had 6.02 times 10 to the 23 atoms of chromium, the average mass of all of that is 52 grams. Values underneath the element, these represent the mass or the number of grams to get the 6.02 times 10 to 23 particles. So we'll do some calculations to determine how many moles of that substance we have, because there's no way that you can count out that many atoms or count out that many molecules. It just isn't possible. So that's why we have these values here. So now we get to use everything that's on the periodic table. We have our molar masses, we have our charges, and we have our symbol. So we're very, very happy now. So the mole and molar mass. Again, since 6.02 times 10 to the 23 is too large to count one by one, this number of atoms is determined by measuring the mass of the substance. So anytime that you ever go into the lab and I ask you, okay, I need a half a mole of, say, sodium, then you're going to have to do a calculation and then weigh it out on a balance or a scale. So, and we do that kind of in everyday life. So let's use an example. For whatever reason, my wife likes us to keep our aluminum cans. It makes her like $2 if I take in 20 pounds or something, but she gets really excited by that. So if I knew that I had 1,000 grams of, say, some aluminum cans, and I knew that each can weighed 10 grams, I don't have to take each can out of the bag. If I know how much the bag weighs, and I put the whole bag with the cans on the scale, I can take the mass, subtract how much the bag weighs, and determine how many cans I have. And we've been doing that. This is dimensional analysis. Oh yeah, we're back doing dimensional analysis. Yeah, is right. So we're going to continue doing dimensional analysis, except we're going to be doing it with molar masses. Okay. So the molar mass, again, is the weight in grams. Where do you get that value? From your periodic table. So again, you have to know your 52 elements, names and symbols, and then we'll do some examples with that. You'll hear me refer to this unit, AMU. It's an atomic mass unit. Don't get overly excited about it. It's actually the same mass as a proton. So that should say proton, not one atom. Proton. Who can remember why these values have decimals, or have we talked about it? Very good. It's all the different isotopes. So we did talk about it before the break, I know. So it's been a while. So that's why it's rare to see values that end in 0.00. This is an odd one. But the majority of them have decimal values because of all the different isotopes. Again, different isotopes mean different numbers of neutrons. Good. So let's do some more conversions here to see if you understand. So the first question asks, how many moles of magnesium are in a 96-gram sample of magnesium? So remember back when we did dimensional analysis or factor labeling, what do you always start with? The information that's given. What's given in this? Actually, two things. Yeah, magnesium, but more importantly, 96 grams. So we start off with 96 grams of magnesium. Okay. Are we looking for grams of magnesium at the end of this problem? No. The question asks for how many moles. So when we look at this, if I look for magnesium, there's magnesium. In 1 mole of magnesium, how many grams? 24.3. Good. So I would say, okay, so my unit grams of magnesium go down here, and I would put 1 mole of magnesium up on top. And we said it was 24 point what? 3. And do we have the unit that we're looking for? Yeah, so we can cancel out grams. And how would you solve for this? That's right, you get your calculator out and do some plugging and chugging there. So 96, get down there. 96 and what'd somebody get?
3.95.
3.95, very good. And what would my units be for that? Moles. And if you wanted to, you could put magnesium on it. However, what I must see is that. Okay. So your unit in this case is how many moles? Okay. Isn't that fun? Let's do another one. So the question asks, how many moles of nickel are in a 25-gram sample? What do we start with? 25 gram, okay, of Ni, and where's nickel at? Nickel's right there, 58.93.
No, it's 6.9.
58.69. Okay, we'll go with that. 58.69, and that's of nickel, and that's in 1 mole of nickel. Okay.
Wait, mine says 58.93.
Whatever yours says, use it. Yeah, I don't know why they would be different, but if they are, just go with what you got there.
Does it not matter?
It matters to a degree. I mean, if you're putting like 158 in there, then we have an issue. So we've got 0.426. Okay. Is everybody getting this?
Yeah.
Okay, this should be the easy stuff. And I hope that it is. Okay. Now, the question's asking how many grams in a 2.5 mole sample of copper. So what do we start with now? 2.5 moles of copper. So how do we do this? So copper is not being shown. So 63.55. So where do we put, what do we do with the unit mole? Move a diagonal, very good. So in 1 mole of copper, what would we say it was? 63.5. Yeah, so 63.55. And what should my unit be here? Grams, good. So 2.5. So around 159. Okay. My calculator says 158.875. Okay. Think you could do that?
Yeah.
Yeah, that's not bad. And we need to do a couple more here. Oh, I know. All right, so that was finding the molar mass of just a single element. We can do it for finding a compound. Okay, so a compound is a combination, and generally speaking, it'll be a metal with a non-metal, but it could be anything. So again, we're going to add the molar masses of all the elements within that compound to get its molar mass. Okay, so like if I had, say, nitrogen dioxide, I have 1 part nitrogen, so I find the molar mass of the nitrogen, and I have 2 parts oxygen. So what I would do there is I'd multiply my 1 mole of nitrogen times 14.01, and then add it to the 2 moles of the oxygen and get my total mass. Isn't that easy? No?
Because I didn't even understand that.
Oh, you didn't understand that. So you add the molar masses after you know what the formula is. So let's do an example. That might straighten things out for you. Okay, here's a good one. What is this Mg parentheses C2H3O2 with the parentheses outside 2? Very good. Okay. So here's what we get to do. We're going to find out what the molar mass of that is by adding up all the molar masses. So magnesium, how many magnesiums do we have in the compound?
1.
1. So you have, what is the molar mass of magnesium? 4.3. And how many carbons do we have?
4.
4. Very good. So carbon has a molar mass of 12.01. It's not being shown there, but right there, 12.01. So 4 times 12.01. And how many hydrogens do we have? 6 of those. And how much does hydrogen weigh? Very good. And then how many oxygens do we have? 4. And how much does oxygen weigh? 16. And add all that up. So, yeah, let's just see how good you are. Doesn't this bring back good memories later? Anybody get a number?
142.
Yeah, and one thing about molar masses, 142 point, did I say 388?
Yeah.
Okay. On this one, we're not going to round. Okay? On molar masses, don't round because generally speaking, you're going to do something with that number. Not today, but we will in the future. Okay? So on that one, leave it as is because generally we'll do something with that value.
Are we done?
Now we get to do the next one.
Oh, okay. Yeah.
Yeah.
This is easy. There we go. Thank God.
But everybody understand that.
Yeah.
That makes sense?
Yeah.
And again, it's mainly looking at your periodic table and asking yourself, well, how many of each do I have? So looking at that, aluminum. Aluminum's 26.98. How many aluminums do we have?
2.
2 of those. So 26.98. And how many carbons? 6 of those, good. 12.01, awesome. And how many oxygen? 12 of those. Good. And well, give everybody a chance to type that in there. Mercy. I hear that. Okay. Oxalate's not one of your 52, but what is calcium? Ca. And actually oxalate is at C2O4. And oxalate has a -2 charge. So how would I write calcium oxalate if oxalate has a -2 charge? What's the charge on calcium? Your periodic table, don't guess. That's why you have it in front of you. +2. Don't guess. There's no reason to guess on something like that. So if the oxalate is C2O4 and has a -2 charge, is that balanced as written?
Yes.
Good. Okay, so you still get to balance. That's why I said make sure you know how to do all this fun stuff. So calcium, 40.08. And how many calciums do we have? One. How many carbons do we have? 2. How many oxygen? 4. So what is that, 128.1? What is that?
I got 128.24.
I got 128.1.
TI
Oh.
wouldn't lead me down the wrong path. Okay. And one more, the iron 3 sulfide. I'll let you try this one on your own, but how would we write iron 3 sulfide? What's the charge on iron here? +3, good. And sulfide? -2, but let's see, what's the symbol for iron? Fe. And we said that it has a +3 charge. And how do I write sulfide? Very good, just S. Okay, it ends in IDE, and again, so is that balanced as written? So we need a 2 there and a 3 there, right? Okay, so again, balance your charges. And don't peek up here, Alan, don't look up here.
You like that?
207.88. All right, so let's blow it up a little bit.
Go down.
All right, so looking at, we'll say the first one. If you have 1.6 moles of, what is Hg again?
Mercury.
Mercury, very nice. And so what's this whole compound called?
Mercury nitrate.
Nitrate. Does mercury have more than one charge?
Oh yeah.
Okay, so this would be mercury 2 nitrate. Good. Just giving you practice. So as you get more and more exposure to this, just ask yourself, what are these names? So the first thing that we want to do, well, actually, no, we can combine it all. So start with what you know. So 1.6 moles of mercury nitrate. Okay. So what unit do we need to get rid of? Moles, very good. So we're going to get rid of mole of mercury 2 nitrate. But how in the world are we going to figure out what that value is there? Do the same thing that you did in the first section. So we're going to find the molar mass for our mercury nitrate. So let's go to the periodic table and find mercury. Mercury, where are you? Right here. Mercury 200.59. So 200.59 grams plus, how many nitrogens do we have? 2 of those, and nitrogen's 14.01. How many oxygens do we have? 6 of those, and how much does oxygen weigh? Just to show you on the table, oxygen's over here. 16, there's the nitrogen. So 16. Now, what I like to do is, I like to actually find out what this molar mass is first, just at the beginning, just to make sure, and then use that number in my calculator. Okay, so let me do this, 200.99. So my molar mass for this is 324, and again, I don't want to round that number. Anybody else get that number that cares? Okay, and then, so I'll take that number, which is in my calculator. If you have an answer button, or even just hit times, should pop up 1.6. And what do you get? Anybody get a number? 519. And that one we would round to 3 sig figs. 519? Anybody else get that? My calculator says 519.376.
Yeah, mine is too.
Just plug it in all at once.
Absolutely, you can plug it in all at once. If you plug it in all at once, how should you plug it in? Yeah. Whoop. Yeah, so if you were to plug this all in at once, the best way to do that would be 1.60 times, open up the parentheses, and then you can just do this because order of operation, 200.59 plus 2 times 14.01. Don't put parentheses in between all of that. Okay? Don't do that. Plus 16, or sorry, 6 times 16. Then close the parentheses, and it should give you that. Okay. You got lucky. That'll change when you put this down here. Okay, so if I started off with a mass amount, which I'll do later on, maybe. Where's the grams? Oh, there we go. So when you do the grams, actually let me do one of those for you. But here's how we would type that in. And I would, for the molar mass, I would just put the whole molar mass in parentheses. Okay. Let me do the first one on the back side, where it says how many moles of each do we have. Okay. So here, let's look at number 1 here, 64 grams of water. What do you start with? 64 grams of water. Okay. And what are we looking for? Moles. Okay. So what goes right here? 1 mole of water. And what makes up 1 mole of water? We have how many hydrogens? 2, and that's 1.008 grams. Plus, how much does oxygen weigh? 16 grams. So all of that is 18.018. Okay, and you'll, sorry, 1.6. No. Whoa. 1.6. Oops. Put the pen down. 1.6. Okay. So if you were to type this in on your calculator all at once, then you would want to go 64 divided by, open up your parentheses, 2 times 1.008 plus 16. So again, the molar mass, everything in there, you don't need to, don't put other parentheses in there unless you wrap it all in a separate set of parentheses. So. So 3.55?
Yeah.
Okay. All right, everybody good now? And that is moles. So make sure that you're also putting your unit on